Do you have a question?
Yes.
What's your question?
My question is moment of inertia.
Hi, I'm Max.
I'm Doug.
And today we're going to tell you a little bit about moments of inertia, stable and unstable rotations, and give you a little history lesson on the Explorer 1. Let's have some fun.
Okay, this is a typical demonstration of moment of inertia. So you have an object, the rod, that has a mass at one end. And then you ask a person to balance it, either with the mass close to their hand or with the mass further away from the hand. And you ask, which way is it easier to balance? Now the typical answer is, well, when the weight is lower, it's somehow more stable. In fact, it's easier to balance this way, as Max is demonstrating, versus the other way. So Max is pretty good at balancing it, but he's also okay. So why is this? Well, when you balance it with the mass further away, the object has a larger moment of inertia, because what it's trying to do is it's trying to rotate out of your hand. And so the mass is further away from the pivot point. It has a larger moment of inertia, so it rotates slower, so it allows you time to catch the thing as it starts to rotate out of your hand. When the mass is lower, it has a smaller moment of inertia. It actually rotates more easily and more quickly, and so you have less time to sort of catch it as it starts to rotate away. Right, Max?
Right. As we continue our discussion about moment of inertia, the next topic we want to consider is the tennis racket theorem. The tennis racket theorem explains an object that has three distinct axes of rotation. Will have three different moments of inertia, and whether or not moving around those axes will have a stable or unstable tumbling effect. So the first axis would be the short axis, the axis that would go the shortest distance down the center of the object. This would have the longest moment of inertia. The mass of this object is furthest away from our center, or from our axis of rotation. Next, we would move on to the long axis, one that would go about the longest line of the box, and this would be a small moment of inertia. The mass is very close to the axis of rotation. The final one to consider is the intermediate, where the axis goes along the medium side of the box, the medium length, and rotations are about this point, where the masses are intermediate distances from the axis of rotation. As we make this object rotate about its short axis, having the large moment of inertia, if we were to rotate it perfectly around this axis, it would maintain a perfect rotation. But if we were to deviate that slightly, it would have a wobbling effect that would wobble around that same central point. We would call this a stable rotation. The same stands for the long axis, with the short axis of or the small moment of inertia. Again, a perfect rotation leads to a perfect rotation around the axis, where a slight deviation would again cause a wobbling effect, but a stable rotation. For the last axes, the intermediate axis, this is not true. If we rotate it perfectly, it will maintain a perfect rotation, but if we have any slight deviation, it'll continue to wander, and that axis of rotation will move, not staying near where we begin rotating the object. We see this when we rotate the box as we toss it in the air. We also see this with the tennis racket that we're about to demonstrate.
Okay, now that we've discussed rotations about of a solid body about 3 axes, we want to move on to a real-world historical example. And our real-world historical example that we want to use is actually the first U.S. artificial satellite, the Explorer 1, which has been drawn up here. So the Explorer 1 was essentially a flying cigar. It was a cylindrical-shaped object which NASA decided to stabilize by spinning around its long axis or its smallest moment of inertia. So much like you stabilize a bullet by rifling it. So, but NASA was actually surprised that after some point, the Explorer stopped spinning around its long axis and small moment of inertia, but started rotating around its short axis, large moment of inertia. Why was this? So there's actually something different that happened in the case of the Explorer as compared to our simple tennis racket theorem demonstration, and it was this. The Explorer actually had flexible structures on it and so forth, and so it actually was losing energy due to internal friction, dissipation, and so forth. So the kinetic energy of a rotating body is actually given by this formula. The angular momentum squared divided by 2 times the moment of inertia. The angular momentum is actually fixed, but the kinetic energy has to decrease. And so the way that that can happen is if the Explorer switches from rotating around its long axis, small moment of inertia, to rotating around its short axis with a larger moment of inertia. If you have the same angular momentum, but a larger moment of inertia, the kinetic energy decreases, which is actually what had to happen. And so this actually is a way of globally explaining why the Explorer went from rotating around its long axis to around its short axis. Now the actual explanation of this in terms of forces and so forth is actually very complicated, but that's the beauty of the energy method of getting at this. You can basically see why the Explorer had to flip from rotating around this axis to rotating around this axis.